Hello everybody, Mikael here, and I'm gonna talk a bit about functions in the C programming language, how they work, what we can do with them, and well, basically stuff around functions. So I have a short agenda here. Well, the agenda is short, but the slide presentation is a bit longer. It's all about functions. And this material in general comes from the chapter 4 in the C programming language book that is called Functions and Program Structure. So let's just take general overall about functions. They are here to break the programs into smaller pieces. So they are here to help us organize the code. Without functions, we would just get a long program. And those are really hard to sort of maintain and develop. So basically, functions help us to organize the code and, well, build better programs in that sense. They can return values. So a function, that small piece, in general it returns some kind of value to us. It doesn't have to return a value, so it can be a void function, but in general it returns a value. It can have in and out parameters, and this in and out, it's not really like that. I'm going to show you an example of it, but in general we can send parameters into a function and they can sort of be copied into the function and just used, consumed by the function, or they can also change the value of the parameter. And so after the function is called, that particular parameter's value was actually changed by the function. So we want to be dry and organize the code in functions, and dry here is a kind of software philosophy called don't repeat yourself. And that basically says that we shouldn't take copy paste of our code. When we do that, instead we should use functions to sort of be able to reduce the code. When we have a lot of functions, we can organize them into files. And then we could sort of think of these files as modules. Modules containing both a lot of functions and maybe variables. But these are sort of, for some reason, they fit together in some kind of module that could get a name. And when we do these modules, we organize the code into header files and source files. And we're going to review some examples on how we can do that. Let's start with the basics of the main function. It's, well, you've seen it before. Here it's int main, and the name the main name is specific for this C program. It's the C compiler must have a main defined because that is where all execution in the executable will start. So here we have it. It will have a return value, integer, and this one also takes arguments. These are specific arguments for the main function, and these are used when we sort of sending in, when we execute the program, for example, on a terminal, then we send arguments into this program here. So the program can get the arguments from the external environment, and it usually looks like this then. It's saying int argc, that is the number of arguments sent. And then there is a sort of a char array that will contain all the arguments. Otherwise, just a small main function, and it's returning a value. And about this return value here, that is basic an exit code of the executable. So this is the final return value when this program executes, and it will be then the exit value of the process, so to say. So it's a common understanding that the exit value of 0, that sort of says successful. So any other exit value would say that this is an unsuccessful program in that sense. So a program generally returns a 0 or 1 is a common way of saying, well, I did some failure, or 2 perhaps. So I'm just using 42 here just for the fun of it. And this is an example where I execute the main. Here I have my program is called main, executing it, just printing it out. And on the second part there, I'm printing out the exit code. So my $ question mark is a way of, it's a variable basically for the terminal, for the Unix terminal, and it contains the value, the exit value of the last process. So here it's turning out to be 42 then. That is Unix specific, but you can try out echo $last exit code on the Windows PowerShell and you should get the same value there. Let's see how we can create the function. So in this example here I have my main and I have slightly rewritten it. I have a variable there saying it's integer status, and I'm assigning status from the return value of my print hello function. So when I have this, the print hello function must be declared, and it is there. And then I'm having this return value status, so I'm just returning and giving the exit code there. Okay, and then we can see that I've moved up some code up to the print hello function. So print hello should return an integer. It has a name. It has no parameters. Just doing printf and returning a value. So this is a simple way of how to organize your code into functions and more functions. You can also declare a function that I'm doing at the top here. So I'm declaring it. I'm not yet implementing it. I'm just declaring it, defining it, saying, well, it's going to be a function called print hello that returns integer without any parameters. It's going to be here. Somewhere it will sort of be implemented, but not currently here. So I'm only declaring it. So when the main function up there is going to sort of return print hello there, then the function must be declared. So it must be defined. So we must know that it will be available for us later on. So, but I don't really need to have its implementation. I just need its function signature, and then I can use it. So this is a way of separating the, declare the function. This is the function that will be here, and then I write its implementation. So let's see another example on how I can organize my code using the functions here. So I'm going to show you an example where I split the code into files. So I'm going to have my file here, main.c, and I want to have a real sort of small, slim main file. So I put all my functions into other header and C files. So, but I still have to have the sort of the definition of the print hello function. I need to have that. And I'm going to put that in the file hello world.h. So let's see what that contains. It should contain the definition, or if I say declaring of the function, but not the implementation of the function. Thus declaring this is the signature of the function. So this is the header file, and I label it hello world. And then I match it with an hello world.c, and here I write the implementation of the function. I also, for best practice, I would say I do include my own header file. It's not really needed since I'm sort of implementing the whole function here, but it's good. It makes me sort of get the feeling that hello world.h contains where I define the function, and here I implement it, and the signatures should look the same, otherwise I would get some error. So it's a nice way of doing it like this. So this is then the way to build modules and add, well, more functions into these modules. This is the general way of sort of separating the code into files. When we compile this then, So now I have two C files. So I need, well, I don't need to compile them separately, but this is the way I usually do it. So I start by compiling my Hello World C file to an object file. Then I compile the main program to an object file. And then I link these two object files together and create an executable that I call main here. And well, this is the way I sort of compile each C file on its own, and then I link all the object files together. So the basic thoughts when we work with functions, that's what I would say. I would like to keep my main function very clean and slim. So I tend to put very little code in my main function. So I put out all the other code I put in functions. And I try to have my functions small, like 5-10 lines or so. Try to make them not bigger, and when I get too large functions, I in general try to sort of organize them into smaller functions, and that usually can be done in that sense. Small functions are easier to maintain, develop, troubleshoot, so that's how I like it to be then. Do not repeat code, use functions instead, and as a good tip or hint here, a function should do only one thing. So when you talk about your function, when you name your function, it should be very clear that it only does one thing. So you shouldn't say that my function does this and that and this, because that means that your function has, well, several areas of responsibilities, and that is not, that may result in a bit more complex code. So try to keep a function small, and it should do one thing and not many things. We talked a bit about dividing the code into H and C files, and if we can relate to this module.c, module.h as a sort of a lib or a module file. So and we try to build these, organize this, so they are sort of self-contained, isolated. They only contain code that is sort of have a strong internal relationship. So I put variables and functions that sort of forms some sense where I can label them with one name, so they are tied together. And that's how I'm thinking of when I'm organizing these modules. I'm not putting this function and that function. I'm putting them in a module on some randomized ways. I try to think that they fit together. Then I link them together, as we saw with a module.o, but I could also create something that is called a lib. So we have a lib module. I'm going to show you how to do this. I'm going to create what I call a lib module.so, so it's a shared object file. And then I'm going to link it with -l and the module name. So let's see how this works. And this is a way that you want to work when you create a larger library or a larger module that someone else or yourself is going to reuse. So it's a bit more structured way of creating bits and pieces for your sort of C programs. So let's see what we do here. So I'm still having this hello world, so I haven't changed its source code. I'm just compiling it in another way. So here I compile the main.c to object file first, and then I compile the hello world C, so the module file. And this time I do it with the -fpic. So this compiler flag, it will compile my code with something that is called position independent code, pic. And this will make that this O file will be able to sort of work in a more flexible sense. It can sort of be added onto an executable, and it's basically about how that object file, the code in it, is organized. So it's organized in a sort of, well, position independent code. It can be used in various different positions in different executables. So this is to prepare my object code to work in a library. And the row 3 here is where you have minus shared. That is where I compile the lib hello.so, so the shared object file, from the object file. And I'm saying that this should be a shared library. Could be used as a shared library. And then at the last step there, I'm sort of linking together my main executable from the main.o object file, and I'm linking with the library -l hello, and this -l hello, it references what is called on row 3 there, lib hello.so. So lib hello.so is the same as -l hello when I'm linking it. The -l dot flag there, that is a library path. So I need to have that to say that look for the library files in the current directory where I am. The dot is representing the current directory where I am. So here I'm sort of showing an example on how I'm building and using a library file for shared libraries. So that is one way of sort of delivering your module to others. This is an example where I'm actually using this sort of, or executing the same program I've just built. And the first there, I get an error. And that is why I get this error, because I compiled my main executable with a shared library. So the shared library would only be loaded when I execute my program. So the loader of the program will see that my program is depending on the lib hello.so, so it will look in all its places where the shared libraries are to try to find that file, but it can't find it up here. So I fixed that on the second part here. So this is also a Unix system, and by saying to the LD library path environment variable and saying, well, look in the current directory, and then execute main. And there you got. So the loader uses LD library path to find the lib hello.so that's in the current directory, and then execution works. So do note that this was an Unix example, so should look a bit different if you were on, for example, a Windows station. But it's just a way how to show where you can create these library files and how you can sort of make your executable depending on them. You could also, of course, create link this library as a static executable. So basically copy the whole library into the executable and deliver it. It will be much larger, since it will contain both the executable and the library, but we won't get these issues with finding the shared libraries. So shared libraries or a static executable. So let's see, go back to functions and do some basics. So here I have a smallest function returning nothing. Returning nothing since it's a void, and it's called dummy, it takes no parameters, and it has no body. But still, this can be compiled, and it's rather good to know that I can do these functions. Because if you're thinking of, let's build a larger program where you want to get a start of it. So you create a bunch of empty methods that you can call. The methods do nothing yet, you have no logic in them, but you're still trying to sort of do some pseudocoding, creating a working application, just creating a lot of placeholders where you want to put in your code later on. So this is one way of sort of not perhaps troubleshoot, but sort of design how you are working when you are creating your application, and do it with small dummy functions or small placeholders. Here is an example of how the function is returning a value. So we see 3 examples, and we see to the most left we see the type that the function is returning. So we got an integer, we got a float, we got a char. And then we can see how the value is returned, 42, 3.14, or as a character. So functions may return a value. Functions can also take these parameters, and we will soon have a look on how the parameter list will look like. But just before that, try to separate. I will try. I mix these together, so I'm a bit bad on this, but still, let's try. So parameters, they are the placeholders, pp. So parameter is the variables in the declaration or the call of a function. That is the sort of holder of a value. The argument, however, is the actual value. Argument, actual value, AA. So when the method is called, the arguments are the data that is passed into the method's parameters. So it could be good if we try to separate what is a parameter, what is an argument, but people around you will most likely mix these together, so they use them interchangeably, meaning the same thing. Well, we tried at least to try and separate them. So parameter is the placeholder. The argument, that's the actual value. So here's an example where we define or create a function up there, and we should return an integer. It's called sum. It takes a parameter list with 3 parameters, and it's returning the sum of these 3 parameters. All are integers. So a function can take 1, 2, or many parameters. Just declare them and declare the type and give them a name. Here is the main function, and it's just showing off how the sum is working. So we declare 3 variables there, and then we call the function down here. Down there we call it, and we send in the... So the arguments in this case would be 1, 2, 3. That is the actual value sent in here. So we are sending KLM as parameters into the sum, and there we calling the parameters A, B, C. So try to sort of remember what is the argument and what is the parameters here. Arguments, the actual value being sent. Parameters, that is the placeholder, so that is the variables that are holding the actual value. Parameters here are also passed by value, that stated down there. So the value that is sent into the function, they are sort of copied. So it is passed by its value. The value is copied. So it is not the variable that is sent into the function, so we cannot change the content of the variable here. We cannot change the content of KLM down here. It is just their content that is sort of copied into the function. So that is good to know, that C is passed by value. There is something that is called passed by reference, but that does not exist in the C language. Passed by reference is in general used when we are sending a variable to a function. The function may update the value of the variable, and after the function call, the variable contains the updated value. So we can do this in C, but it is not called pass by reference. It is basically called pass by address, and we solve this using pointers. So we will learn more about pointers in another sessions, but let's just quickly review how this example is done. So here I have a main function, so it contains two variables, and then I call the update functions, and I'm sending in here, as you see, I have the apostrophe ahead. So this is the address of K and the address of L. I'm sending in the address into the function. And I need to do that since I want the actual value of the variable. I want that to change. So I'm sending in the address. Here the value is stored, so please change it. And then I have implemented my function up here. So I created my function, and it takes a pointer to an integer. And these two pointers, I then will change the value that the pointers points to. And by doing this, mixing the address, sending in the address using a pointer, I can actually sort of update the actual value that these variables are holding. But this is not, in general, sort of a pass by reference. It's the same, may work equal, but we in general call this pass by address. So the general output of this main function would be K is 2 at the start, L is 4 at the start. So then I would do update. So K is incremented, L is decremented, and then once again. So K will have a 4 and L will have a 2 after this sort of execution is done here. So just a note again on the pass by reference. So C language is pass by value without exception. So passing a pointer here that I do as a parameter, that does not mean pass by reference. So let's call it pass by value, pass by address perhaps. There is something called variable parameter list. So this is how you could create a function that takes, well, unlimited or undecided amount of parameters. You can declare it as up there. So you got an int sum, and then you declare the first variable, and I declare it for this sense. I'm saying so int argc. So this in my implementation is holding how many values should I sum. It doesn't have to hold that type of value. It should just hold some kind of value that will help you understand how many items is it on the parameter list for you. So when I'm sort of basically using it here down, so I'm going to sum, and I'm saying, oh, I'm going to sum 5 values for now. And then I send in 5 values, K, L, M, 6, 12. So it's 5 values I'm going to sum. So let's see how we implement this sum function. So we need to get some assistance to be able to do this. So we are including standard arg here. And while doing that, we get ahead of some, I think it's macros here. It's the VA list. So let's see what I wrote here in my comments. So the first thing I need to do when I'm sort of trying to access this variable parameter list is to declare some kind of argument pointer. So I declare it first, and then I initiate the argument pointer up there. And then I'm sort of using my loop, since the argc, which is the first and defined variable, I know it's 5 because I sent it in, and that should then contain how many numbers I must sort of sum. So I can create a loop going through this, and I use va arg to get each of the arguments in the list, and I also need to know what type they are. So there are integers here I'm going to sum. And when I've done that, I've summed it all together. I'm going to wrap it up with calling va end. And this is sort of the basic steps so to be able to sort of create this type of variable parameters list. And if you think of it, I think if I just go back for a quick one there, and you see this printf function, if you think of it, this is also implemented in this way, because the first string there, you always have to have a string to printf. It contains this %d, And this %d, when sort of the printf function scans this first string, it's okay, now I should get an integer. So it knows that the variable parameter list should contain one integer and nothing more. So this is also the printf and scanf. They are examples of how the C program is using variable parameter list to sort of, well, makes it a bit flexible, if you say so. Let us see a bit about the scope rules and how scope is used. And scope is about visibility of functions and variables, or visibilities of the sort of, items being declared. So when something is declared in function, it has a function scope. So it's visible all through that function. When you declare something, variable for example, on a file level, well, that variable is visible for all functions in that file. And we in general call this, it's a global variable because everybody will see it in that file. And it is not only visible in that file, because if someone else declares that particular variable that you have in your file as extern, then you can be in another file and still saying, okay, I know there is a global variable somewhere in some file, I don't care where, but I'm going to declare it as extern here. So you declare it as extern, and then you can use it in any place in this executable. So it's for sure a very global variable that we create then. So this was function scope and file scope, and even sort of the global scope. I have done one example here, and I'm using it to illustrate how the extern definition of variables is working. So basically I have a main.c, I have a module.c, and I have a module.h. And then I have 3 variables. And these 3 variables I'm going to declare in 3 different ways. So for the first one here, you see I'm declaring the string main here, giving it a value. So this is a global variable in this file. And then I'm sort of declaring an extern char string module.c, and that says somewhere in this executable there will be some char pointer called string module.c, and it will have some kind of value, but it's not declared here. Then I'm also sort of referencing a module.h string down there, so that would most likely be declared in the module.h file, and yes, it is. So here we see that the string module.h is declared, but it's still extern, so it's not implemented here, it does not get its value here, it's just sort of, yay, somewhere in the code it will be a string module.h with a value, but not here. So it's basically declared in the module.c file. So here we have it. Here we have the value for the module.h. We also have the value for the module.c. And we even trying to use the value declared in the string main here, in the main.c file, the variable called string main. So all these 3 values can be printed out here also. So this is a way to visualizing how the sort of global variables can be accessed from anywhere in the program. So that might be good, or that might also be bad. You need to be aware of that. This is the way it works. Okay, so let's see another use case, variable scope. We have something that is called static local variables. So these are, in general, initialize them once, and then they remember the value. So even if we declare the static local variables in a function, they will remember the value from each call to the function. So that could be good to have for some time. So this is an example of showing how the static int, I'm declaring it there on the top. So static int inc, and I'm initializing it to 0. And then I'm printing its value, and when I'm printing its value, I'm also going to increment it by 10 each time. Okay, so down here in the main program, I'm actually having some kind of loop. I'm looping from 0 to 7, it looks like 7 times, and I'm calling the memory function. So this function up there is going to be called 7 times. The first time the variable inc is initialized, and then it's incremented for 10 each time it's called. So how would the output for this execution look like? I give you 5 seconds to think about it. And then we go to the answer. So this is the output, and it's just showing that the memory function kept its value between each call to it. And that is how a static local variable is working. The static keyword can also be used on a file variable, and it can also be used on a function. So the functions and the variables on a file level, they are global objects. So what we can do with this static keyword is to restrain the visibility of these declarations, both for a variable and for a function. So they can only be visible within this file. So it's kind of protecting them, restraining the visibility so others cannot see them. So if I do this, like we have the last example here with the external char string module C, meaning that this is defined somewhere, but then I change my const char string and I put a static in front of it. And that static would actually prevent the main C here from declaring that as an extern, so it can't read it. So this is a good way when you have modules that you want some parts of the modules should be sort of private property to the module and shouldn't be able to be used outside of this particular file. And then we declare it as a static variable or function. So again, this static can in this sense hide the token from other files. So functions and variables on file level, they are this global object in the symbol table. But when we declare them as statics, we make them sort of local only in the file they are declared in. So this avoids name clashing, where the variable or function names might clash between many modules. And it also gives you some possibility to define your module and use your own names on both the functions and the sort of variables you have there. And only the sort of the functions that the user of your module will sort of use, that is the public API of the module. So they need to be declared not static, but the other ones can. So I would say it's a good practice when you work with modules or libraries that use static whenever it's sort of whenever it's needed. Do so. Quick note on the register variables. So these are used to advise the compiler that the variable is heavily used in calculations. So we put the register class, variable class in front of it. This is just a recommendation to the compiler, and we're basically saying, hey, I got a variable here that is heavily used in calculations now. So if you can have the opportunity to put it in the register, I think it would be a good thing, but I won't force you. Basically, that's what it's saying. a note on block structures and scope. So functions contains blocks of code. So we usually have one large block of code that is the function and the function's whole scope. But the function can also introduce new blocks, new blocks of statements. For example, in if statement, switch statement, while, for loops will introduce these blocks of statement. And each new block with these curly braces, each new block introduces a new scope. So in each new scope, we can actually create new local variables, and they will be used within this sort of block scope only, will only be visible in this sort of inner block scope. So variables declared in these blocks are local to that block or function. So this is an example program showing you how one can sort of shadowing a variable by declaring a new variable with the same name. So here I am having a main, I declare integer up there giving its value 42, and then I'm printing it outside. So that will for sure be 42 printed. Then I'm having a loop where I declare a new variable, integer e. I give it value, initialize it with value 0, and then I'm going to print it inside the loop. Okay, so what type of value will I get there? Well, most likely, or for sure, the value of I here that goes from 0, 1, and up to 2. But what will be the final value here when I'm getting back outside of that loop? So now I'm outside again, and I'm going to print I. What will be the value? Will it be 42? Or will it be 2? Well, let's see. So we see here that outside is the 42. So we have basically two variables having the same name in the same function here. But since they are on different scopes, that the first outside variable, it contains for the function scope then. And then I declared a new variable local to that block, the for block. And that was only visible there. And then when I'm sort of out of the for loop, I'm back on the outside. And then I have the old variable keeping its old value. So this is good to know that this is how it works. The variables and the block scopes. When we do initialization of variables, they are initialized different depending on what kind of class the variable are. So here we're saying that the external and the static variables, so external and static variable classes, they are guaranteed to be initialized to 0. Okay, good. But the auto and the register variables, they have undefined garbage values. So if we do not initialize an auto variable, which is in general all variables, since that is the default variable class, then it will be undefined. And that depends, it works like this depending on, since, well, the storage for the auto and the register variables, they in general have some other value before. And if we don't initialize that with a new value, it will sort of be, well, the last value it had there. So garbage, that is. The external and static variables must be initialized with a constant expression. And they are only initialized once, and they are initialized before the program even starts to execute. And that's why they need to have a constant expression. You can't call a function and returning a value to an external or static variable. They are initialized even before program execution starts. The auto and the register variables, they can be initialized with any expression function call, and they are initialized each time the block where they are declared and when the block is entered. So each time the block is entered, they will be initialized for new. Let's talk a bit about recursion. So a recursion of function, that is when a function is calling itself. So this could be sort of pretty useful when you are sort of solving some kind of complex algorithm and you see, oh, wouldn't be, okay, my functions solved part of the problem. But if I call my function again with a new value, it might also solve the other part of the problem. So then you have some kind of recursiveness where your own function is calling your own function to solve the algorithm. If we try to consider the Fibonacci sequence, the Fibonacci sequence is a mathematical sequence of values, numbers. It starts from 0, goes to 1, goes to 1, goes to 2, 3, 5, 8, 13, and 21. So these are the first numbers in the Fibonacci sequence. And the basics behind it is that each number is the sum of the two preceding numbers. And the whole series should start on 0 and 1. So this means that if the series starts on 0 and 1, so the first two numbers are given, and then I take the the 1, 2, 3, 4 figures, the third number, 1, 2, 3, the third number, and that is a 1. So that should be the sum of the two preceding numbers, and that is a sum of 1 plus 0 equals 1. Okay, good. Then I take the 2. That should be the sum of the two preceding numbers. 1 plus 1. Yes, that's a 2. And then I take the 3. That should be the sum of 2 plus 1 equals 3. Yes. And for the last one, the 21, that should then be the sum of 13 plus 8 equals 21. Okay, so yeah, I got it. Let's see if we can sort of, how would a recursive solution look for solving this sort of Fibonacci sequence? This is just a way to sort of visualize the Fibonacci sequence, and it's in general this Fibonacci sequence is sort of trying to show a natural way of working with numbers where numbers relate in size to each other's. Could be used in sort of design, providing a pattern for how one section in size should relate to another section. If you maybe you heard about the golden ratio, and that's those sort of stuff. But let's leave the design area out of this, and let's go into this recursive solution for the Fibonacci sequence. So I got a main first, and I'm going to calculate the Fibonacci sequence for the first 10 numbers in the sequence. So I'm creating a loop, calling my Fibonacci function, and I'm calling it, so I'm calling it with the sequence number. So first I'm going to get for the 0 position, then I'm going to get for 1 position, then I'm going to get for the second, third, fourth, fifth, sixth position, and so up to sort of, well, 10 positions here. So how is this Fibonacci function implemented? So let's see it. Here it is. So it's declared there, returns an integer, takes an integer I. So this is the sort of position in the sequence it takes in. And what we have here is that the sequence, if I equals 0, then we know it's going to be a 0, because the sequence starts at 0. If the I is equal to 1, then we know it's going to return a 1, because that is also given in this Fibonacci sequence. But then for all the other numbers, we need sort of to calculate the sum of the two preceding numbers. And that could then be sort of nice way of doing this in a recursive sense. So we are returning the values, but we are calling the Fibonacci function again with -1 and -2. And well, then it's going to continue down until the sort of function may return a value, and we can eventually sort of calculate the Fibonacci sequence. So this is just showing you a function can call a function, and that is what we call recursiveness. This is the output of the program when I execute it. So we see that 10 the sort of the 10 starting values of the Fibonacci sequence calculated, starting from 0, 1, and then it just goes on. Okay, good. We haven't reached the end yet. We have a few things more to talk about, and the C preprocessor is one of them. And this will help us understand a bit about the first compilation step, that is sort of preparing the C code to be compiled. The first compilation step, or the preprocessor, results in C code general, but it's sort of putting together all the bits and pieces of the program and creating this sort of C code down. It does this by including the files. So the C preprocessor is taking the include instruction here, and it's including the system files and my own include files, and sort of basically copying the whole include file right into the sort of the whole block of code that is going to be compiled. It also does something that's called macro substitution, and that is all the defines that we have created, where we define that this name should be replaced with this construct. The C preprocessor does this, so it sort of replaces the macro substitution, we call it. So define we have, and we could also do undefines, just good to know for now. And this is also one part where the C preprocessor is working. This is called a conditional inclusion, and this is generally a pattern or template for how we write our include files. That it is basically it's checking if the module.h is defined. If it's not defined, we will define it, and then comes the content of the header file, and then it's an end if. So it's an if statement. It's a conditional way of saying that as long as this sort of token is not defined, yeah, then I want to execute this part. When this token is defined, I will not execute it. So this sort of prevents an .h file from being included many times in our code. So it could be good to have this common sense to write down this, sort of wrap up our header files like this. Okay, so let's see how this macros is working. Here I have a macro, so I've defined a macro, and you see I did a macro here, max, that are basically taking two arguments, so max A and B. So it looks a bit like a function, but it is a macro. And this macro, max A and B, will be replaced with this ternary operator, conditional expression. You've seen it before. So it's basically just a construct expression to calculate the max value of two values. So on the second one here, I'm this is my C code where I use the macro with two values, and I'm gonna so the max value of 7 and 9 gonna be put into the variable A. And then I run the preprocessor, and this is what the actually output will be of the program after the preprocessor is executed. So it will sort of, well, you see it. I got the define up there. It found the max macro, and it substituted it with the code I have for the define up there, and there we see it. I can show you how this sort of looks like. It's always fun, I think, when we're learning new languages to see how it works and looks behind the scene, because it provides, at least for me, it provides the understanding on how a language works. So let's see how the preprocessor works with how will this code look like when we have run it through the preprocessor. And we can use the compiler flag -e to actually see it. So, okay, do you remember the code? Good. Let's move on and see how the C preprocessor creates it. So we can just skip the top rows here that is commented and see the main file here. And then we see that the macro substitution has been done. And you can also see here where the 7 has replaced the 9, 7, 9. So macro substitution, that is how it's working. And if you sometimes get unsure on what's actually happening, well, remember you can use the compiler flag -e to see the result from the C preprocessor. It'd be a nice thing to sort of check out sometimes. And one of the final things I'm going to talk about today will be the stack. And it generally relates to functions like this. When a function is called, when we call a function, the data about that call is pushed to the stack. The data will be sort of the location of the call in your program, the arguments of the call, the local variables of the function being called. So all this put together is this data. It's a block of data, and this is called a stack frame. This is the stack frame for the current execution of this particular function, a stack frame. All the stack frames are allocated onto the stack. So when we execute our program, we have basically two places to store memory in. We have the stack and we have the heap. So this is the stack. So when we call functions, when we declare variables in blocks, all these are put onto the stack. If we take an example, just to sort of further show off how it works. So let's say we have a function b, and we are currently in the function a, and we're going to call the function b. So what are the bits and pieces that is actually happening? And this in general, this is what I'm going to show you is just a generic way of sort of how this could be done. This will most likely differ from system to system and some reason, but we just want a general view of what is actually happening when I'm calling a function. So I'm in function A and I'm just prepared to call the B function. So the first thing, before I'm actually going to the B function, I'm going to prepare some stuff. So I'm going to push the space for the return value. So that I'm going to push onto the stack. I'm going to push the parameters onto the stack. So these are the actual parameters sent to the function. And then I'm going to push the return address. Where should we return once the B function is done? And when that is done, I do jump to the B function. Good. So now I'm in the B function. So first I'm going to prepare a bit stuff. I'm going to push the address of the previous stack frame, because the previous stack frame for A, good to have when I'm going to go back there. And then I'm going to push the values of the registers. Just to be able to restore this later on when I'm done. I'm going to push space for the local variables, and I'm going to declare in my function, and then I just do my work, necessary computation of the B function. And then I'm done. I'm preparing to leave, so I'm going to restore the registers. I'm going to restore the previous stack frame that is preparing me to jump back to A. I'm going to store the function result, the return value, and then I'm going to jump to the return address, that was available on the stack for me, so I just got it, and I'm going to jump to the return address. And now I'm back in function A. And back in function A, I can pop the parameters, and I can pop the return value from function B. So that is the way of how a function call is done and how that relates to storage on the stack. And these things are very good to know to understand the basics. And when you later on come to debug your code, perhaps you want to sort of examine what is currently on the stack. There in the current sort of stack frame, you will see the value of the local variables. So good to know how the structure of this are. So we are actually trying to wrap this up. To sum it up first, we did a lot about the functions today. So we talked about how the basics of the function works, how to sort of try to think when we organize them in modules, how that works with header files and C files. We talked about the bits and pieces of the functions like arguments and parameters. We talked about the function's return values. We talked about these scoops. We need to know about how scoop is working. We talked about the block structure, the block scope, function scope, and how different variable classes also relates to these scopes. We got an example of recursion, always nice to see that. We talked a bit about the preprocessor of C, so it included the files and did macro substitution. And then we talked about the stack and how each new call will be sort of pushed onto the stack with its stack frame and the related data. Okay, so this was basically what we talked about today. And this is the final part where I'm gonna say hello and thank you for watching this part of functions, and I'm sure I'm gonna see you sometime soon again talking more about the C programming language. So until then, bye for now. Bye bye.